Well, hello there. Welcome to the next version of thermodynamics. Today we're going to be talking about properties and phases of fluids and how we can find those. Um, I've got a little bit of a head start here, so I'd like you to go ahead and catch up. The first thing we're going to do is draw up the temperature entropy diagram so that we can look at the different phases of a fluid. Then we're going to talk about enthalpy. So you go ahead and draw, and while you're doing that, I'm going to get busy down here simplifying this equation. Okay, so the temperature entropy diagram is a visual way for us to look at the different phases of a fluid. We call this black dome-shaped thing here, we call that the vapor dome. And underneath the vapor dome, we have a mixture of liquid and steam, or liquid and vapor. Um, to the right of the vapor dome, over here, everything is a superheated vapor, and to the left of the vapor dome, everything is a subcooled liquid. So let's see if we can figure out what that means. Well, this blue line that I have right here is called the line of constant pressure. And if we were talking about water at atmospheric pressure, so 14.7 psi or 101 kilopascals, and then we're talking about boiling water. Well, we would start with a liquid. Think of putting a pot of water on your stove, and it's a liquid, and its temperature is less than boiling. What is the boiling point for liquid? Anybody know? 212, you say? Oh, very good. So the boiling point is 212. Well, if we have a liquid that's at 80 degrees or 150 degrees or somewhere down here where my mouse is, it is called a subcooled liquid. Let me grab another color here, and we'll put that in. We actually use the symbols SCl for subcooled liquid. As you keep heating up your pot of water, it gets to 200 degrees and 205 degrees. And then when it gets to 212 degrees, it gets to this point right here at the left of the vapor dome, and we use the symbols, the letters S, L. We call that a saturated liquid. A saturated liquid is 100% liquid, but it's at the boiling point, 212 degrees, for your given pressure, and our given pressure is 14.7. If our pressure is different than 14.7, then we'll have a different boiling point than 212, and we'll talk a little bit more about that in class. If you keep putting heat into your water, at this point the bonds are going to start to break, and you'll have a mixture of liquid and vapor. And as you have that mixture that goes from 0% vapor, 100% liquid, to down at this end, 100% vapor, 0% liquid, we change the phase and we call that SV for saturated vapor. And everywhere in between, we call a wet vapor. So far we've got 4 phases of the fluid: subcooled liquid, saturated liquid. Subcooled liquid is a whole region. Saturated liquid is a point, exactly when the temperature and pressure of saturation go together and you're on the vapor dome and you have 0 vapor, all liquid. Saturated vapor at the other end is a point. Again, same temperature and pressure match, but 100% vapor and 0% liquid. Wet vapor is a region, and it's in this region that we introduce a new property called the quality. And grab another color for quality. And the quality goes from 0% steam quality to 100% steam quality. That's not a very good color there. Let's try that again. We'll just set it right on there. All right, quality. There's one more phase, and we call that a superheated vapor. So imagine you've got your water on your stove, you heat it up, it goes from liquid to beginning to boil, partially boiling, 100% boiled. Now if you keep putting energy in, the energy is going to go to taking the steam to a higher temperature, and up here we have what's called the superheated vapor. And that's a region up there. So those are the different phases. What we're going to end up doing is using something called the steam tables and these phases to find the enthalpy for a fluid at a given point. And once we can find the enthalpy, we can find out how much heat is transferred in, we can find out how much heat is transferred out, we can find out how much work is being done. So enthalpy, all about that H, it really is important. So I've started working down here with the first law, just the way we've seen it in the past. In engineering, we often take and realize that the potential energy and the kinetic energy are quite inconsequential. So we can cancel them out. So we're left with the internal energy plus the heat in, plus the work on, minus the heat out, minus the work by, equals the internal energy. It turns out that there are 2 kinds of work. There's something that we call shaft work and something that we call flow work. And so if I take work and say there are 2 kinds, shaft work plus flow work, and I deal with this term called flow work. Flow work is actually pressure times volume. Pressure times, what should I use for the times? We'll use that, times specific volume. When I go back into the first law, I'm going to let work on be shaft work on and work by be shaft work by. And I'm going to have to account for this flow work in the first law. I'm going to press pause, type that up, and then put it into place. So look what I've done here. I've taken the work term, broken it up into 2 parts, shaft work and flow work. And I'm going to let work on be the shaft work, and then P1V1 be the flow work. Same with work by is the shaft work, P2V2 is the flow work. Enthalpy is a convenient grouping of the internal energy and the flow work. Let's type that in. Enthalpy is the convenient grouping of internal energy U and flow work P times V. We use the symbol H. So enthalpy is the convenient grouping of internal energy and flow work. H equals U plus PV. Why are we doing this again? Because enthalpy is the most important property when figuring out how much work is done or how much heat is being transferred in an engineering process. It's by far the most important. We'll see it in refrigeration cycles, in internal combustion engines or diesel engines like in your cars or in a power plant. It is the most important of the properties. And so I'm going to go ahead and rewrite the first law one more time now with the H's. So here we have the first law. It's got enthalpy, heat, work, on and in, heat, work, out and by, equals enthalpy. So the amount of energy transferred is equal to the change in enthalpy. In our next video, we're going to learn how to go into something called the steam tables, and given any pressure or any temperature or any entropy or any quality, find the H's. Then once we can find the H's, we can find all sorts of energy terms. All right. Well, thank you, and we'll see you in class.